Hi guys, I'm Hedgeberg. Hope this video finds you well. This is going to be lecture 4 in my analog design lectures video series. Today we're going to be talking about what I think is probably one of the coolest pieces of material that I learned in my first year of undergrad, which is going to be, sorry if you guys hear people in the background, that is my partner shouting at our cat who is being a bit of a jerk. We're going to be talking about frequency domain. Oop. That's a terrible. I don't want to start off with my terrible handwriting. Ideally, we'll decay into that later in the video. Frequency domain analysis. Before we get started, I want to go ahead and cover what we talked about in the last lecture. But first, I have two quick footnotes. First of all, right. Sorry, before I keep going, this is actually going to be lecture 4A, likely because of the fact that I am putting a hard 45-minute stop on these on this lecture, because this one's going to go for a while, and there's a good chance there's at least an hour and a half of material, and I don't know if I have the chops to talk for an hour and a half straight without any kind of break. So I'm splitting this into two parts, and hopefully I'll get the second part up tomorrow. So when I talk about what we're going to cover in this lecture, I mean between the two parts, 4A and 4B. So previously... Oh, right, sorry. Other thing that I meant to do. First of all, I record these videos in one take. If there's some mistakes, that's why. And two, this lecture and all of my other lectures are brought to you by my patrons on Patreon, patreon.com/Hedgeberg. If you like these videos, consider supporting me. I would appreciate it. Thank you. Okay, so previously we talked about energy storage elements. Which are inductors and capacitors. And then we used first order ordinary differential equations to understand time domain response and finally we talked about exponential decay. If you don't remember what any of those are, I would really recommend going back and watching the last lecture. We will not be using first-order ODEs in this lecture, but there's a good chance that they'll come back up again later, and we are going to be talking about the rest of this. So let's talk about what we're going to cover in these two parts of this lecture. Now, the first thing that the overall theme of this lecture is going to be understanding the frequency domain. To understand that, though, we're going to need to know a few other things. I should say, we're going to be using the frequency domain to understand filters, or we'll use filters as a way to explain the frequency domain. Both points are kind of the central theme of these frequency analysis lectures. Before we can talk about those, though, we need to talk about this cool guy named Fourier, also known as Fourier, also known as Fourier. I've heard all of those be called correct or incorrect at different times. I'm going to stick to what I learned when I was learning this, which is Fourier. He was a Frenchman. I do not remember when he was alive, but we will talk about what he did and why it matters in just a second. And we're going to be talking about impedances. So let's go ahead and get started. So I'm going to make a new layer. I'm going to mute our last layer. And let's get started with talking about impedances. So when we, in the last lecture, we talked about a relatively simple looking circuit, something that took a step function input and dissipated it across a resistor and used it to charge a capacitor. And after a lot of complicated math, we got that V out as a function of time looks something like this, with t equals 0 here at the origin. V, t, and we decayed something like this. This was exponential decay, and we would, stop at a horizontal asymptote here. It took us a lot of math to get to this point. In the last lecture, which was an hour and 10 minutes, we solved 2 circuits like this. We solved one with an R and an L, and one with a C and an R and a C. Solving 2 simple 2-component circuits in an hour and 10 minutes is way too slow. These circuits are complex and they're hard to solve when you look at them in the time domain. That becomes a problem. So ideally what we'd like to look for is a simpler way to solve these circuits, something that allows us to look at multiple stimulus, things like that. So we're going to go ahead and start talking about something a little weird. Basically, when we first learned about resistors, one of the really neat tricks that we learned was the voltage divider. R1 and R2. And so, if you have V in and you have V out equals VR2, this is equal to V in times R2 over R1 plus R2. The voltage divider is a really simple way to look at circuits like this and get a simple output voltage. What if we could translate this simple method to work on this circuit as well and give us the information about the output voltage? Well, we'd be able to skip all the differential equations first of all. But to do that, we need to know the resistance of a capacitor. The issue is that a resistance is fundamentally a property of a resistor. There isn't a resistance of a capacitor, but there is a unifying property, which is called impedance. And we symbolize that with a Z. When we told you that V equals IR, Ohm's law, we actually were telling a little bit of a lie, to be totally honest. This is a very simplified form. This works for resistors, but the reality is that Ohm's law is V is equal to I Z. Sorry, I didn't mean to put that little hook on the I. You can ignore that. So the voltage is current times impedance. The reason this works like this in the simpler form, V equals IR, for resistive circuits is that the impedance of a resistor is equal to its resistance. The reason for this will become pretty clear pretty quickly. Basically, we're going to go ahead and take a second to define impedance as it relates to resistance. Z, or impedance, is a few things. It is a complex number. Hopefully you all know what those are, but if you don't, it is a sum of a real number and an imaginary number. So, in the case of impedance, it is R, the resistance, which is a real number, plus JX. R is the resistance, X is the reactance. Together, they make impedance. When I say J in engineering notation is the imaginary number. A lot of times in math, you'll see the imaginary number represented with I. J equals I equals root -1. So, in this case, we're going to be using J. I don't know why this is the convention that engineers chose to use, but it is. So we have z is a complex number, and it is also frequency dependent. Specifically, x is a function of omega, where I should note that omega is equal to 2 pi times the frequency. We'll go ahead and get into more details on what all these terms are in just a second. But knowing that V is equal to IZ, the good news is a capacitor and an inductor also have an impedance, meaning that we can actually use the derivation that we applied to get our voltage divider for our RC circuit here. Let me go ahead and get rid of that because I'm going to want to upload these as notes. So Control Z. So check this out. What we actually get now is V out is equal to the impedance of C over the impedance of R plus the impedance of C times V in. Okay, great. So all we have to do is do this simple voltage divider using impedance instead of resistance, and we've got our answer. Except, what is the impedance of a capacitor? What is the impedance of an inductor? It's not just R, it's something else. And it's not simple, unfortunately. And so now, if we want to understand that, we have to go ahead and talk about Fourier. There's a few things that we need to remember here as we start talking about this, and why we're talking about this specifically. First of all, you have to remember that since x is a function of omega, this is lowercase omega, by the way, this w, I know it looks terrible, but this means that z is also a function of omega. When we've talked about capacitance and inductance, we've used the equations IC is equal to C dV dt. So the current is C times dV over dt. And for an inductor, V is equal to L di dt. Basically, their current is, or their voltage and their current are based on the rate of change of the other. Knowing this, it is in fact possible to get to an impedance which is frequency dependent. And that's thanks to Fourier. So let's talk about Fourier. Fourier had a theory. He claimed that all real signals can be represented as a sum of sinusoids. What does that mean? Basically, Fourier demonstrated that any signal, any real-world function, whether it's a square wave or y equals x, all of these real functions can be turned into frequency components. This concept is actually used in all kinds of things. It's used in image analysis, it's used in video compression, it's used all over the technical world nowadays because it is fundamentally incredibly powerful. Basically what this means is, let's go ahead and give an example. Let's say that we have y equals sine of t. This is the sinusoid or this is the sine of t in the time domain. If I recall correctly, sine starts at 0. Yes, it does. In this case, then, the frequency of this sine wave is 1. F equals 1. Here, let's say we had sine of 3t instead. That would look something like this. So we'd have 3 periods. 2, 3. And I'm going to stop drawing so it doesn't get more complicated. Basically, the idea is, you know, there's 3 periods in one of... Oh, geez, I screwed that up real bad. Apologies, folks. 1, 2, 3. Good enough. Basically, we have the same thing, but 3 times faster. Here, the frequency is 3. What Fourier demonstrated is that these signals can be represented as frequency components. So, for example, if we have y as a function of t is equal to sine of t, then in the frequency domain, this would look something like this. This is, I should say. Oh, it's not letting me control Z. Weird. There we go. I guess it's because I still had the create a layer window open. Okay. In this case, if we have y magnitude and we have f over here, so f is frequency, then here for f equals 1, you'd have an impulse with a magnitude of 1. And for f equals 3, if you have this other one, this sine of 3t, instead, because the frequency of that is f equals 3, then the impulse would be at 3 instead. So an impulse with a magnitude of 1 and a frequency of 3. If you added these two signals together, you would get this for your response instead. So a simple example is sine of t plus sine of 3t. The Fourier transform is one impulse at f equals 1 and one impulse at f equals 3. What we've done is we have turned a real-time signal with values all the way from negative infinity to positive infinity into a representation with just 2 impulses. This is the case of magnitude. There is also phase. But this is something that we can get into as we go a little bit farther forward. I'm going to be doing some hand waving here because I don't want to get too far into the bits and bytes of frequency analysis. It is a course full of details all on its own. It is incredibly complex. There's stuff like the reality is this signal is actually reflected to the negative orientation as you go from 0 towards negative infinity for frequency. It's complicated. So I'm not going to get too far into it. And in fact, I believe that this is actually a little bit wrong because of the fact that this should be 1/2, if I recall correctly. It's weird, and it's a little hard to understand. And to be totally honest, I don't remember it as well as I wish I did. But I want to give you guys the basic qualitative understanding, so that way as we move forward, it kind of makes sense. This method can be used for any signal. This can be used for any real signal that occurs in nature. Any continuous function has a frequency domain representation that is a sum of sinusoids, including something wonky like a square wave. So, if we have a square wave like such, in the frequency domain, a square wave is a sum of sinusoids. It is the sum from I equals 1 k equals 2I plus 1, or no, from I equals 0, sorry. No, it is I equals 1 and it's 2I minus 1 up to infinity. A square wave is the, if I recall correctly, now that I'm thinking about it, I do not remember it as well as I want to. And I'm sorry about that. I should remember this better, but I don't. It's been a long time since I did this. It is something along the format of 1 over 2 pi k times the sine of kx. This creates a frequency domain representation f v that looks like this. It's a set of impulses at the odd harmonics with an envelope of 1 over x. The idea being here that you can represent a relatively complex function using basically a set of coordinates. It's a very, very simple way of representing information. There is a way to transform between the time domain and the frequency domain. And Fourier called that the transform, and we call that the Fourier transform nowadays. And the idea is something like this. X as a function of omega is equal to the integral from infinity down to negative infinity of x as a function of t e to the negative j omega t dt. So, as I said, we're not going to go too far into Fourier transforms because I am out of practice. That's not what this lesson. It's not what this lesson is about, and the math is very tricky. There's a lot of steps to this integral, and frankly, calculus isn't the point of this course. If I make another course about frequency analysis and signal math, I'll get this all right. I just want to give the qualitative overview. So don't quote me on any of this is the point. Please don't quote me on any of this. I barely remember it right now. But this does give us a tool. If you remember, we want to transform this I equals c dv dt, a time domain dependent function relating voltage to current, into something that's frequency dependent so we can use impedance. So you want to turn this into z of omega. Now we have a tool to convert between time domain and frequency domain. So we can actually convert this function here into something like impedance. So we're going to go ahead and we're going to come over to another slide and we're going to start doing the following. I'm going to use capacitance as an example, and I'm going to basically set up the integral and then skip the integral to give us what the impedance of the capacitance of a capacitor is. I'll then go ahead and write down what the impedance of an inductor is, and I will leave the exercise of the integral to those who choose to do it, but it is not necessary for the purposes of what we're doing here. Basically, we're going to go ahead and derive what's called a phasor. Here we go. So, starting off, we're going to go ahead and say that we know I equals C dV dt. We're going to go ahead and multiply both sides by dt equals C times dV, and we're going to integrate. This will give us I times t equals C times V. Now, we're going to go ahead and divide both sides by C, and we get V equals I times T over C. So, if you remember the format of our impedance model in Ohm's law, we have V equals I times Z. So we have this in mostly the right format, except for the fact that this is time dependent, not frequency domain dependent. So we need to go ahead and make that translation. So what we do is we treat current as constant, voltage as constant, and we say V is equal to I over C, which is also constant, times the integral from infinity down to negative infinity, t e to the negative j omega t dt. So now we're going to pause and we're going to skip doing this integral and jump to the result. If you're interested in doing this integral yourself, you need to understand a few things. You need to understand how to break e to the negative j omega t into its sine and cosine portions, which is another signal processing simplification that I don't want to get into now. And if I can't derive it, I don't really want to be doing much of it during these lectures. I want to keep this as intuitive as possible. So knowing this and knowing that this is the conversion, what we get is V is equal to I times 1 over j omega c. Now, we know that V equals IZ, therefore Z is equal to V over I, and in this case, Z is a function of omega I should say, which means that here, Z sub C as a function of omega is equal to 1 over j omega c. We now have the frequency-dependent impedance of a capacitor. Before we keep going here, I want to try and make sure that this is intuitive in how it works. Basically, a capacitor builds up charge on its plates. What this means is that how much of a resistance it supplies is dependent on the frequency it's exposed to. So, as the frequency goes higher, the magnitude of this 1 over j omega c term decreases. In this way, a capacitor becomes less and less like a resistor to high-frequency signals. We'll talk about what that means in a second. This is where this stuff does start to get kind of complicated, and it's why this lecture is going to be broken into 2 portions. The other thing that we talk about is Z sub L of omega. And so this is the impedance of an inductor, which is J omega L. So we now have our impedance for our inductor and our capacitor. Again, these are frequency domain dependent. but this means that we can actually analyze our circuits in terms of how they respond to frequencies. So let's go ahead and move on to the next portion, which is going to be using this. Give me a second to go ahead and actually jump back to my title slide to make sure I'm covering everything I mean to be. Frequency domain, filters, Fourier, impedance. Yep. So we've talked about a little bit about what the frequency domain is. We've talked a little bit about Fourier. We've talked a little bit about impedance. All of this moving relatively fast into this specific derivation, j omega c and j omega l. We now know the impedance of a capacitor and the impedance of an inductor, and we can begin to analyze circuits in the frequency domain. Let's go ahead and explain more in depth about what that actually means so that we don't lose anybody here, because I have a feeling that if I were watching my own video right now, I would probably be lost. So let's go ahead and start a new slide. And what we're going to do here is we're going to go ahead and start looking at some RC circuits. This is going to be a filter. There are two things that we want to look at when we analyze this circuit in terms of its phasor components. So we mentioned phasors earlier, and I should mention that what a phasor is basically the difference between, how should I explain this? A phasor is basically using complex coordinates to represent phase and magnitude in polar coordinates. Yes, that sounds extremely confusing. So let's go ahead and make sure that all of this is explained. Hopefully, if you're watching this, you've taken enough trigonometry to know what polar coordinates are. If not, the quick way of summarizing it is that instead of mapping stuff using x and y, you map things using r, the radius, and theta, the angle. So, in polar coordinates, where you would have, or in regular coordinates where you would have x and y, your coordinate 2 comma, or your, what am I doing here? X, y, stupid, would be 3, 2, 3 comma 2, oh, 3 comma 2. To represent this in polar coordinates, you would represent it with its r and its theta. So here we have r, which is the length of this line from the origin to the point, and you have theta, which is this angle. So what we have here when we deal with complex numbers is basically x and y coordinates. And to get our magnitude and phase, we're going to say is phase is the time offset of a sinusoid represented as theta in phasors. Magnitude is the amplitude of a sinusoid represented as R in phasors. I'm going to go ahead and do some picture drawings now to try and make that a little bit clearer, so that way we know what our terms are before we get into this. This part does get tricky, so please try to follow along. So phasors continued. Earlier we mentioned magnitude and frequency. There is also one other property, which is phase. Here, if we go ahead and say that y equals blank sine of blank t plus blank, in the basic case, let's just go ahead and say this is 1, this is 1, this is 0, and you just have sine of t. There are 3 ways to adjust this function. So let me go ahead and plot sine of t real quick. We have y, we have t, so this is 2 pi. So let's say that we want to go ahead and shrink it horizontally from here to here. So that way, instead of landing at 2 pi, we'll maybe land here instead after this first period. And I should go ahead and add that this is 1 and this is -1. In that case, then, we would adjust this term. So here, if we're landing at 1 pi, we would have 2t. How quickly we can get through a period is the frequency. The other thing that we'll deal with, or the next thing that we'll deal with, is, go ahead and erase this. The next thing that we'll have is y t magnitude. So instead of going from 1 to 1, let's instead go from 0.5 to -0.5. So this would look like this. Oh, that's... Oops. In this case, we've adjusted the magnitude by multiplying this by 1/2. So here, we have our magnitude, which we'll represent with capital A. The last thing is phase. And phase is represented by shifting this over to the right, to right here. So in this case, I'm going to go ahead and erase this one more time to make it. I don't think there's really a good way to make this clear without making it a little bit messy, to be totally honest. And I'm sorry about that. Ooh, I just changed my eraser to a pencil. I'm not the best with tablets. So let's say that instead we start this over here. We've shifted the phase by pi over 2. So here is where we go ahead and modify phase. So here, this is going to be theta. Between frequency, amplitude, and phase, you know the components of any frequency. When we do frequency domain analysis, we basically analyze amplitude and as a function of frequency omega, and phi, not phi, theta, as a function of omega. So, phasors allow us to do this, I'm not going to say easily because it's still tricky, but they give us an easier way to deal with it. What we do is we analyze things in terms of complex numbers. We have, if you remember impedances again, Z as a function of omega is equal to R plus JX. These are X and Y coordinates. Here is our real axis. Here's our imaginary axis. So here we've got our reactance, X. We've got our resistance, R. Together, these plot a point here. Then, from that, we know that the amplitude is the length of this guy, what we would call the hypotenuse of this triangle, and theta is the angle. Phasors give us a way to represent a signal at a given frequency as its amplitude and its phase without having to use polar coordinates. This means that we can use a lot of the math that we already use without having to get overtly complicated. We can represent sinusoids as simple coordinate points. So, what this means is that A of omega is equal to if we have something like V out equal, so let's go ahead and give an example. Actually, let's go ahead and give the best example I can give, which is an RC circuit. Yep. And if this is making your head hurt a little bit, it made my head hurt when I was first learning it too. And I really honestly wished I had asked questions. I'm really going to suggest that if you have any questions, you come to the Discord that we set up for that specific purpose. I can hop in voice chat with anyone. Just let me know and we'll figure out a time. It's kind of like impromptu office hours. I'm always there. I get notifications whenever somebody posts, assuming that I'm not in the middle of streaming because notifications are disabled from my Discord. Please come and ask questions if any of this doesn't make sense. I know this is kind of an impromptu break in the middle of the lecture, but when I was learning this, I had a horrible time. I struggled with it like you could not imagine. So, let's go ahead and give it a phasor example. We're going to bring back that, we're going to go ahead and bring back our previous circuit that we had from the last lecture, our resistor and our capacitor. But instead, we're not going to give a specific function for V in. We're going to call V in as a function of t, not as a function of t, as a function of omega, an arbitrary function. We don't care what it is, we just care that it exists. What I want to know is V out. The good thing about frequency domain analysis is that we can get an answer for this without ever doing any kind of differential equation. We don't have to worry about what the stimulus is, so long as we know what the frequencies that compose it are. So, the good news is this is literally just a voltage divider. because of the fact that we can use impedances. So we have R and we have C, and that's my 45-minute timer. So let me go ahead and turn that off. And we're going to keep going, and we'll resume next lecture with more examples of this, more discussion. I'm going to try to have that out probably tomorrow if I can. I don't know if I have time right now. I'm in the middle of a job search, which makes things a little bit difficult. So we have R and we have C. So we know V out over V in is equal to Z sub C over Z sub R plus Z sub C. Oh, nope, not R sub C. That's my bad. So we know that the impedance of a capacitor is 1 over j omega C. We know that the impedance of a resistor is R, and we have the impedance of the capacitor again, 1 over j omega C. What we need to do here is fairly obvious, I think. We have to go ahead and simplify the top portion. So we multiply the top and the bottom by j omega C. So we get 1 over 1 plus R j omega C. So we can go ahead and get the frequency domain behavior, and we can go ahead and get the phase behavior from this. But before we do, let's go ahead and just think about it at an overarching level. We're not going to think about phase. We're just going to think about magnitude. Specifically, magnitude decreases as frequency increases. For omega equals low, we'll say on the order of, so we'll say omega is much less than R. If omega is much less than R, then R j omega, or if omega, I should say, if omega is much less than RC, then this term is much less than 1, which means that this simplifies to approximately 1. So let me go ahead and put this down here so we can make a little table of behaviors. The magnitude of V out over V in is approximately 1. Let's say omega is equal to 1 over RC. Then we wind up with V out over V in is equal to 1 over 1 plus J. If we take the magnitude, it's equal to 1/2. If we keep going like this over time, wait, is that correct? Yes, that is correct, I believe. I could be wrong. I'm pretty sure that's correct. Basically, if omega becomes much larger than RC, then V out over V in terms of magnitude, is dominated by 1 over 1 plus, we'll call it, I don't know, 1,000. The point being, it's large. It's exceptionally large, meaning the imaginary portion overpowers this, and we wind up with approximately 0. So before we ever do the actual analysis here, before we ever actually get the numerical analysis going in terms of magnitude and phase, what we have here is we have a circuit that at low frequencies V out is approximately V in. When we get close to 1 over RC, V out is half of V in. And as omega gets higher, V out drops lower compared to V in. What we have here is something that gives a behavior like this. Let's see. Wait. I feel like I'm doing something stupid here. Right. It's going to look something like this. This is 1/2. This is frequency. This is magnitude of V out over V in. At, nope, that's not 1/2. I'm doing that wrong. This is omega equals 1 over RC. I should be doing this on omega, not F. And this is 1/2. Around here, it's close to 1. Here, we fall down to 1/2. Here, we cut off to 0. What we have here is something which allows low frequencies through and removes high frequencies. We have a low pass filter. This RC circuit, as frequency increases, filters out more and more of the frequency. This means that low frequency examples go through, high frequency samples do not. This means that if a signal is composed of high frequency components and low frequency components, this RC can strip out the high frequency components and just let the low frequency components through. And we choose what frequency we cut off at. With omega is equal to 1 over RC. So F, because nobody works in omega in reality, is equal to 1 over 2 pi RC. F cutoff, which we typically recognize with F0 or F sub C. Sorry, give me a second to do a quick stretch here. What we can do then is choose the frequency at which we cut off by choosing R and C. We're not done with this. There's a lot left to be explained here. There's a lot I have to think about how best to explain it, honestly. I still don't have the second part of this lecture planned out, but I know that there's some details that I want to go into. So, we're going to go ahead and stop here for now. And when we come back for part B, we're going to pick up right from where we left off. And what we're going to go into is some clarification of this. We're going to talk about how we describe phase, and we're going to talk about better ways to think about this. Because this is still relatively complicated. It's still not simple. And what we'd like is a simple way to think about this. So what we're going to do is we're going to go ahead, we're going to call it, and when we come back, we're going to talk about how we can make this simpler and how we can apply it for given frequencies. We're going to talk about magnitude and phase and the easiest way to convert between phasor domain and frequency domain. Hopefully this all makes a fair bit of sense to people so far, but I also know that this was something that I struggled with a lot as a student. And so if this doesn't make sense to you, now is a good time to ask questions, especially since any questions that you ask will help me design the next lecture. If you have any questions, please do not hesitate to come hang out in the Discord and ask. The link is down in the description. And I will try to have the next video up within the next couple of days. So, if you appreciate this lecture, consider liking, subscribing, commenting, whatever. I'm not gonna lie, I feel a little bit weird about splitting this in the middle. I don't know how much I want to do of this format in the future. I just feel like this is one of those topics that needs to be broken into a couple of parts so we can take stock. I think that's going to be everything, guys. So I will see you in a couple days with part B of this lecture. And when we move on, hopefully everybody will have an understanding of what frequency domain analysis is and why we use it. I'm going to go ahead and go. Thank you so much for joining me. I'm Hedgeberg, and I will see you for part 4B. Have a great night.